Good morning, one and all. Welcome to another session on computer organization. We have been looking into the hardwired control unit design and how different instructions are being executed under the hardwired control organization. Now, we saw that an external clock and the instruction which the user gives are used as input to drive the entire system. So, at different clock pulses or at different time cycles, different operations are done by the computer. When we start with to indicate the completion of one instruction, we have used a sequence counter. The sequence counter can count up to 16 cycles, which is T0 to T15 cycles. It can count, but if we complete an instruction execution before T15, the sequence counter is cleared to indicate that the next instruction has to be executed and the current execution is completed. So we started with clearing the sequence counter, and at time cycle T0 we have to first load the instruction. To fetch the instruction, we use the program counter. We use that address, load that address into the address register for accessing memory, and then when we start execution, we indicate that the next instruction to be executed can be identified at a location program counter plus 1. So at time cycle T0, we load PC into address register. At time cycle T1, PC is incremented and the memory content addressed by the address register is brought inside the instruction register. And at time cycle T2, we decode that instruction. Precisely speaking, bits 12 to 14 of the instruction register go inside the decoder, and then we have seen that bits 0 to 11, which are indicating the address of the operand, they are sent into the address register, and the MSB or the bit 15 of the instruction register is sent into the addressing mode flip-flop I. So I have a flip-flop I. Now, depending on the value of the first 4 bits, I can determine what sort of instruction I have been given or the computer is given. To identify that type of instruction, we have used the decoder's output D7. If D7 happens to have 1, it is because of 3 ones being present in bits 12 to 14 of the instruction register. So if instruction register has got bits 12 to 14 set to 1, only then the decoder's output D7 can be 1. If D7 is 1, it indicates that it is either a register reference or an IO instruction. If the value of D7 is 0, it indicates a memory reference instruction. And once we have distinguished between these kinds, then we can look into the value of flip-flop I to identify exact type of instruction. So when D7 is 1 and I is 0, it represents a register reference instruction. And when D7 is 1 and I is also 1, it represents an IO instruction. And when D7 is 0, it is because it's a memory reference instruction. So the flip-flop I value can be used to distinguish between direct and indirect memory access. So with the value of D7 0 and with the value of I equal to 1, it represents an indirect memory access. So you have to double reference the memory for getting the data value. And if it's a direct memory access, the address is already present in the address register, which we have done at time cycle T2. At T2, if you look in, 0 to 11 bits of the instruction register has already been transferred into AR. So we are not going to do anything at time cycle T3 for direct memory access. With this, we are synchronizing everything at T3, and we start with the execution of any specific type of instruction at time cycle T3. For memory reference instructions, because we require a double reference for indirect memory access, we will start with the execution of the instruction at time cycle T4. So this is what we have seen earlier. So the control information that lends different types of instructions is given here. Now this indicates that if D7 is given as dash, which means D7 value is 0, and it represents a memory reference instruction. And if the I value is 1, I can mention it as I. So D7 dash I indicates an indirect memory access. So you have a reference to the memory which is given as memory content addressed by the address register is now another address value by itself. So that is brought inside the address register. Now the content in the address register is the location where I can fetch the data from. So that is completed at time cycle T3. And the second one which is given here, it's wrongly typed in your book. This is scanned information from your book, but it should be D7-I-T3 when I value is also 0 and D7 value is also 0. At that point of time, at time cycle T3, we do not do anything. So we maintain that clock pulse without any operation. And when D7's value is 1 and I value is 0, it represents a register reference instruction. And when D7 value is 1 and I value is also 1 at time cycle T3, we execute IO instruction. This is what we have seen in the previous sessions. And we started with our register reference instruction. So when we look into register reference instruction, we commonly have the control information as D7-I-T3. So it always happens when D7 is 1, I value is 0 and at time cycle T3. So that we have taken as a common predecessor for all this control information and we have given it as R. And then based on the 12 bits of the instruction register 0 to 11, we do some particular operation. So depending on which bit is set to 1, we can perform the respective operation. For example, the first instruction CLA indicates RB11. RB11 indicates that the bit 11 of the instruction register, which is the 12th bit from LSB, is B11. If that bit alone is set to 1 and if the rest of the bits are 0, then it indicates a clear accumulator operation. So likewise, we have looked into 12 different instructions under the register reference category. And then we moved on into memory reference instruction. Memory reference instructions always take place at time cycle T4 because at T3 we are doing a double reference for indirect memory access and we are not doing any operation for a direct memory access. With that, we synchronize both direct and indirect memory access so that the execution is commonly done at time cycle T4 irrespective of whether it is a direct memory access or an indirect memory access. Now, with that in mind, these are the instructions we have seen earlier. Now, for an memory reference instruction to be executed, the operation code is specified in the instruction register from bits 12 to 14. This is given as an input to the decoder circuit, which we have seen earlier. If you remember, this is the decoder circuit that we have seen. So bits 12 to 14 of the instruction register, which indicate the opcode, are given inside the decoder, and the decoder lends an output of D0 to D7. D7 bit is set to 1 only if it is a register reference or a IO operation. For all other for all other values of D0 to D6, it represents only a memory reference instruction. So here we will use that information and see if the output of the decoder D0 is set to 1, we perform some memory reference instruction. All the other values will from D1 to D6 will be 0 at that point of time. And if D1 is set to 1, we perform add operation. D0 will be set to 0 at that time. D2 to D6 also will be 0 at that time. So the decoder's functions such that only one of its output will be high and the rest of its output will be 0. So when we have this idea in our mind, we know when D0 to D6 represents 7 different operations, that can be executed. So these 7 operations are given as memory reference instruction. For any memory reference instruction, one of the data value is from memory, the other data value is from the accumulator by default. If I have a write operation, I send it into memory. Now, when we do that operation, we should remember that the data register serves as the gateway to any memory reference instruction. So, any data that is brought out of the memory is always through the data register. And when you every time you read something from memory, it is always accessed by indicating its address in the address register. So address and data register form gateways to the memory unit. But if you have something to be written into memory, you can directly do it from the accumulator. Only while reading, we need a mandatory data register. So with that in mind, we have executed some memory reference instructions. This is how the memory reference instruction can be shown in the flowchart. For D naught equal to 1, when D naught is 1, it is wrongly printed in your book. The value given to be given here is actually T4. So when D naught is 1 and at time cycle T4, for doing an AND operation, we first bring the data inside the data register. So you have an address in the address register. That memory location is referenced and that data is brought inside the data register. Once the data is available in the data register, at time cycle T5, D naught equal to 1 and at time cycle T5, we perform an logical AND operation with the content of the accumulator and store the result back inside the accumulator. This can be seen here. Once that is complete, it indicates that the execution of that instruction is completed. So I clear my sequence counter. Then the next instruction given here is add. Add is executed when D1 output is 1. All the rest of the D values will be 0. And when D1 equal to 1 and at time cycle T4, what I do is I take the data from the memory location addressed by address register. It is memory of M of AR, not M of MAR. It's printed wrongly. So you have the MAR brought inside the data register. Now the data is readily available in the data register. I have to perform an addition operation. So at time cycle T5, when D1 is 1 and at time cycle T5, I have the accumulator content added with the data register and sent. The result is stored back inside the accumulator. When this is done, if there is a carry, if I have a carry value from the accumulator, it is spilled out into another flip-flop called as Cout. Cout is a flip-flop that is capable of storing a spillover carry value from the accumulator. So it's very closely hardwired to the accumulator. So the MSB of the accumulator, when there is a carry, is sent to a flip-flop called Cout. This Cout is stored in a temporary register. E is always called as the extra register. It can be either the data register or the temporary register. In our design, we have accommodated 2 data registers, right? So one is data register DR and the other one is the temporary register TR. E can represent either DR or TR. So the content of that flip-flop, if there is a carry, is sent to that extra register and stored for future reference. Once I have completed this addition, I indicate that the sequence counter can be cleared off to 0. The next instruction happens when the value of D2 is set to 1. When D2 is set to 1, it indicates a data access. It is a load accumulator operation. When I say load accumulator, I am loading some content from memory location into the accumulator, or the accumulator is getting loaded with some memory value. So this happens at D2 when D2 is 1 and at time cycle T4. I read the memory location addressed by the address register and bring that content inside the data register. And at time cycle T5, the data register content is sent into the accumulator. This completes the instruction. So I clear off the sequence counter to 0. The next instruction is happening when D3 value is 1. It is the store accumulator operation. Store accumulator operation indicates storing of the accumulator's content somewhere inside memory. So I have to now push the content of accumulator into a memory location. Because I already told data register is used only during read operation, when I am sending something inside memory, I can directly do it from accumulator or data register. Both registers are capable of sending data into the memory unit. So at time cycle T4, when D3 is 1, I can directly push the content of the accumulator into the memory location addressed by the address register, which is shown as M of AR receives data from the accumulator. And once this is done, my instruction is complete. So at time cycle T4 itself, I can clear off my sequence counter. So store operation requires only one memory cycle. Now in the rest, when D4 is equal to 1, it represents a branch unconditional statement. A branch unconditional statement indicates that I have to transfer the control of execution from one location to another location. So in the instruction, it is mentioned where I should send my control execution to. So that is given in the 0 to 11 bits of the instruction register, which have been transferred into the address register at time cycle T2. So after T2, I know that there is some address in the address register. So that is the address to which I have to send my control. So from that particular address, I should start executing my next instruction. So that to indicate that when D4 is 1 and at time cycle T4, if the instruction is branch unconditional, D4 value becomes 1. So at this control information D4 and T4, we can transfer the control execution by updating the value of PC using the value which is contained in address register. So the address register content is directly sent into a program counter to indicate that it has to start executing from that particular location. This completes a branch unconditional statement. So you can clear off the sequence counter when D4 is 1 and when cycle T4 is completed. This next operation is called as branch and save return address. We have seen that this is used for so this is used when you have D5 value set to 1 and when T4 is equal to 1 or at time cycle T4, this execution begins. Branch and save return address is used for execution of subroutines. So imagine I have a main program where I have been doing my execution, and this execution can be transferred into a subroutine which is given using some address value. The address value is mentioned in the address register AR. So I have the address value where my subroutine begins, and we saw that for a branch and save return address value, the subroutine address starts from one memory location. The first memory location of the subroutine is maintained as an empty slot, and the subroutine usually begins from the next memory location. Now, because I'm just revising, I'm not drawing it on the board right now. So what I do is, the program counter value has to be saved, which is called as the return address. The return address is saved in the first memory location, which is purposefully left empty by the subroutine. that first memory location, I am saving my return address, and from the next consecutive memory address, I should start my execution. So I increment the address register by 1 and then I transfer it to the program counter, indicating that it should start execution at that point of time. And once the entire subroutine is complete, only then I'll resume to the main program. But a branch and save return execution, the execution of that particular instruction completes when I transfer the execution at that particular location. So with that, I can clear off my sequence counter. I will get back to my main program with the help of a branch unconditional statement placed at the end of the subroutine. So this is how a subroutine in assembly language program works. Now the next last instruction is the increment and skip if 0. Now to do this instruction, let me explain it this way. We will run through the branch and save return address once, and then we will go into the, when I say branch and save return address, imagine this return address is placed in memory, and I have given direct memory access for this, and I place 150. Imagine this instruction is placed in the main program at memory location 100. If it is really difficult for you to follow from here, let me try it straight to the camera so it's easier for you to. So this is my branch and save return address instruction, which is placed at memory location 100. My PC value will carry the value 101 when it is executing this particular instruction. This 101 is the next memory location in the program. So the program counter keeps track of what to be executed next using the program counter. With this in mind, I have a subroutine which is placed at memory location 150. So at 150, I start my subroutine. In assembly programming, the first location of any subroutine is purposefully left vacant, and the subroutine begins at the next memory location. So at 151, I can start with my subroutine instructions. So I have a set of instructions that indicate my subroutine. So when I execute branch and save return address instruction, I have to send my control to this particular location 151. So I should send my execution to 151, and the instruction says that I should save my return address. The return address is the location or the address to which I should come back and start resuming my main program. So this is my main program. After completion of the subroutine, I have to come back to this 101 to resume execution of my main program. So to do that, I have to save this 101 somewhere. So when I am trying to execute branch and save return address instruction, the two things that I need to do are saving this value 101 somewhere and changing the control execution flow to the location 151. These are the two things I have to do when I execute a branch and save return address value. Now once this instruction is completed, then the instruction to be executed is somewhere else. So I will start execution of my subroutine after that value. The two things that I have to do during the execution of this instruction is only to save the return address and change my control flow. So the first thing I will do is saving of my return address. This return address is saved in the empty space which is purposefully left blank at the starting of the subroutine. So first I have to find out this 101 and save it inside the memory location 150. Where can I find this value 101? This 101 is available in my program counter. So this program counter value I have to store in some memory location. Where can I find this 150? This 150 is available in instruction and it has been sent to my address register. So I will load this value of PC into a memory location which is addressed by the address register. So this will be complete. Once I complete this, I have to change my execution flow of control to this particular memory location. I should send my execution to this value. That is indicated by updating the value of PC. Now I should update the value of PC with some other value. What is that value? PC, I have to put the value 151 in PC. 151 is not available. So what I do is, I increment the value of the address register and then put it inside the value of program counter. So it will understand that it should send the control here. So the next instruction to be executed will be found at location 151. So that's how we update the program counter. This is how we execute branch and save return address. Now, only this process happens when we execute the instruction branch and save or BSA. After I complete execution of a set of instructions here in the subroutine, I need to resume back to my main program. To achieve that, I have to use some other instruction inside my subroutine to achieve that. So that instruction is called as the branch unconditional. I have to branch unconditionally back to which location? 100. Where have I saved that 100? I have to get back to the location 101. 101 is the value that I saved in my starting address. So this value 150 is what I have to use. This value 150, I have to go to 150, find out my return address and then go to that location. Because I have to read this and then go back here, it requires a double memory reference. So it is called as indirect memory access. So the value of the MSB is going to be 1. So place an indirect access branch unconditional statement with the first location of my subroutine. It can help me resume back to my main program. So branch and save return address does only two things. Saving of the return address at the first memory location and updating the value of the program counter. To resume execution back to the main program, I have to use a different instruction at the end of my subroutine, which is a branch unconditional statement. Are we clear till here? Now the next instruction which is to be executed, which we have seen, is the increment and skip if 0. In this instruction, what we do is, we read the content from memory. If the content that is read from memory is 0, we are going to skip one instruction and move over into the next instruction. So the first thing is bringing some content from memory. This happens when the value of D6 is 1 and at time cycle T4. So when D6 is 1 and at time cycle T4, I first read the content addressed by the memory address register into the data register. The data register now has received data from a memory location addressed by the address register. At time cycle T5, when D6 is still equal to 1, then we increment the value of the data register. Because the instruction says increment and skip if 0. That is what is ISZ. So I have incremented the content of the data register. It is still not complete at time cycle T5. So I will be using one more time cycle to complete this instruction. So when D6 is 1, till time cycle T6, I am going to continue execution. At time cycle T6, I send the value of data register back inside memory. If the data register is 0, then what do? Then I increment the value of PC by 1. This increment helps me to skip one instruction. Here if you see, 101 is the instruction to be executed next. If I increment the value, so PC will have the value 101. If I make it 102 or increment the value of PC by 1, instead of executing the instruction at 101, it will go into instruction 102. So incrementing the value of PC helps me skip the execution of one instruction. So if data register content is 0, then I skip one instruction by incrementing the value of PC. This will complete the instruction, so I can clear my SC to 0. So this is how memory instructions are executed. So each memory instruction requires different timing cycles. So this is the overall set put together. All the 7 memory reference instructions are given in this flow chart. So from AND, add, load accumulator, store accumulator, branch and conditional, branch and save return address, and increment and skip if 0. So these are the memory reference instructions, and each of these instructions take different timing cycles, unlike register reference instruction. In register reference instructions, we have seen that all the instructions are getting completed at time cycle T4 itself. But in memory reference instruction, the number of timing cycles required by different instructions vary. So from T4, some of the instructions get completed at T4 itself. Some of them extend up to time cycle T6. So you can use any number of time cycles. Once you complete the execution, you can clear off the sequence counter and indicate that you can start with the execution of the next instruction. So with this, I will wind up today's session. We will look into the next variety of instructions, the IO instructions, in the next class. Thank you one and all. Stay home, stay safe. Looking forward to seeing you all soon. Thank you.